Okay, and in this example, we know that 2 plus I is a root of this fourth degree polynomial, so we want to find all the other roots of this polynomial. And just like what we've been talking about, if we're given a root that's imaginary, then we also know that it has to travel in a pair. And so since you know that 2 plus I is a root, then we also know that 2 minus I is a root. Okay, but that's as far as that. When we're going to try to narrow down this polynomial, since it's fourth degree, let's try to get it down to a square since we know exactly two of the roots. Okay. So let's use kind of the concepts up above, and let's pretend like we know for a fact that x is equal to 2 plus I and x is equal to 2 minus I. So let's blend these together and try to create their own tiny little polynomial. So let's move everything over just like what we did in example 3. So x minus 2 minus I equals 0, and x minus 2 plus I equals 0. And then just like we did before, x minus 2 minus I times x minus 2 plus I equals 0. Okay, the x minus 2's match up. We have an I, and here's the conjugate part, minus plus. Okay, so when I multiply these together, I'm going to multiply x minus 2 times x minus 2. The outsides is going to be I times x minus 2. The insides is negative I times x minus 2. And last, a minus I squared. Okay, so what I'm trying to do is just get a tiny little polynomial that just represents these two roots. We multiply this out with those two canceling off. We'll get x squared minus 4x plus 4, and then a minus negative 1. And it looks like it's matching up to exactly, since this is the same one that we had just up there in example 3, it'll give us the 5. Okay, so now what can we do with this to help determine the other roots of the x to the fourth minus 2x cubed polynomial? Okay, well, the math concept that we're looking at doing here is like, let me show you long division. If I divided 3 into 48, okay, so 3 into 4 is 1, just doing the typical. 3 into 18 is 6. So what we know is that 3 and 16 are factors that make 48, or you can consider them roots that make up 48. So what we found out here is that I know that this polynomial over here, this x squared minus 4x plus 5, that together it represents two of the roots. So how can I get the other ones? Well, all we have to do is divide it into the original problem, and it'll give us the other ones. So if I take x squared minus 4x plus 5, and I divide it into my big polynomial, just like I did 3 into 48 to get 16, where 16 was the other root, then what it's going to do is give you my other roots up there in the top. So just being careful, because anytime we do this long division, we need to check to make sure there's no missing terms, which doesn't look like we have, but I just want to check as I write these down. Okay, let's get started. So x squared into x to the fourth, looks like we need x squared. Let's multiply it back through by all three parts. So x to the fourth minus 4x cubed plus 5x squared. Put this in parentheses and subtract. X to the fourth minus x to the fourth is 0. And negative 2 plus 4 is 2x cubed. 7 minus 5 is a negative 2x squared. And bring down the negative 30x. Okay, so start the whole process again. X squared to 2x cubed is a positive 2x. So 2x to all three parts would be 2x cubed minus 8x squared plus 10x. Put that all in parentheses and subtract. So 2x cubed minus 2x cubed is 0. And negative 2x squared plus 8 is 6x squared. Negative 30 minus 10 is negative 40x. And then bring down the plus 50. And just for a second, real quick, I was checking my math. This part right here where I did 7x squared minus 5x squared, I was just looking up real quick, and that's a positive 2 instead. Okay, and then I just want to double check. If I go 2x times all of those, so positive 2x cubed and negative 8x, positive 10. So if we subtract, the fronts go away, and a positive 2 and a double negative on the 8 will be a positive 8. So that should give me a 10. Just want to double check one more time. And then negative 30 plus and minus 10 will be negative 40 and 50. Okay. All right, I hope everything else is right. I just happened to catch that just real quick. But x squared to 10x squared, I need a positive 10. So multiplying it back through is 10x squared minus 40x plus 50. If I put that all in parentheses and subtract, then I should get an answer of 0, which is great because obviously if these were roots of the equation, it had to have a remainder of 0. So that was a good check. Okay, so now to get all the other roots, all we need to do is get them from that guy right there. Okay, so we have a quadratic, just x squared plus 2x plus 10 equals 0. We could try to factor it. There's no factors of 10 that add up to 2. So if we can't factor, remember we always do either completing the square or the quadratic. So I'm going to try the quadratic. So x is equal to negative b plus or minus the square root of b squared, which is 4, minus 4 times a times c, all over 2a. Okay. So x is equal to negative 2 plus or minus the square root of 4 minus 40 is negative 36. So it looks like we're going to be getting some imaginaries again. So negative 2 plus or minus the square root of a negative 1 is I, and the square root of 36 is 6, so 6i over 2. So x is equal to, if I divide this out, negative 1 plus or minus 3i. So those are the other two roots, because the first two were 2 plus I and 2 minus I. So to get a total of 4, the other ones are negative 1 plus 3i and negative 1 minus 3i. Okay, so let's try example number 5. Example 5 says we just want to determine what information can be found out about the roots without actually solving it. So this is what this is referring to is Descartes' rule of signs, is where we want to know the information that they're asking us to really find is how many positive roots, or what are the potential positives and what are the potential negatives, the imaginary ones. Okay, so Descartes' rule of signs basically says that for you to figure out all of the potential positive roots, what you do is you go to the original function, which is the x to the 5th minus x cubed minus x squared minus 3x plus 2, and you count the number of sign changes. Okay, so if I go in here, if I go from, obviously my front term's positive, so if I go from positive to negative, that's one sign change. The next time is negative to negative, it hasn't changed. Negative to negative hasn't changed. Negative to positive changed. So I had one right here and I had one right here. So there were a total of 2 sign changes. Okay, and that Descartes' rule of signs says then always count the number of sign changes and subtract 2 from it. If you can still get a number out that's you haven't gotten to the negatives, then you need to consider it. So 2 and then 0. Okay, and so what we have just found that for this function right here, that if I wanted to go through and do the plus or minus the factors of the back over the front and try to do synthetic division, that at most I can either get 2 positive numbers like x equals 4, x equals 1, or I can have no positive numbers. Okay, so 2 or 0 potential positive roots. Okay, now how to go about getting the negative ones. Okay, so for the negative roots, like x equals negative 3, what we do is we go back to the original function and only switch the sign in front of your odd powers. So odd powers are 5, 3, and 1. So a positive x to the 5th now becomes a negative x to the 5th. A negative x cubed is a positive x cubed. That x squared is not an odd power, so I don't change its sign. 3x has an odd power, so I'm going to change that now to a positive 3x, and then plus 2. So only switch the signs in front of the odd powered ones. And let's count. Okay, so from negative to positive, there's 1. From positive to negative, there's 2. Negative to positive, there's 3. And positive to positive, not so much. So we've counted 3 sign changes, and the rules say take that number of sign changes and subtract 2. You always just subtract 2. So 3 minus 2 is 1. If I subtract then, again, I get down into negatives, so I'm not going to consider it. So these are the potential negative roots. Okay, but what we want to do to really answer this question is we want to give it in terms of like almost a total chart. So here's my positives, and then I'm going to have some potential negatives, and then we also have imaginaries as an option. Okay. All right, so here's how we're going to list them out. I know for my positives that I need to do a combination of these. I could have 2 positives, 3 negatives. I could have 2 positives, 1 negative. So matching up 2 to 3, 2 to 1. Or I can have my 0 positives with 3 negatives, 0 positive with 1 negative. Okay, so 2 matches to 3 and 1, and then 0 matches to 3 and 1. Just kind of comparing those. Now, since the overall degree of this whole polynomial was 5, then I know I have to be getting 5 roots, no matter what. So if I go through each row should add up to 5. Well, 2 plus 3 is 5, so that means that if I go with this combination, there's going to be no room for imaginary numbers. It's going to be 2 positive, 3 negative, and that's it. If I go to the next row, though, 2 positive, 1 negative, that means that the other 2 that were left over had to be imaginary, because each row has to sum up to 5. Okay, it has to equal the total degree. So if I had 0 positive, 3 negative, then 2 imaginary, and then 0 positive, 1 negative leaves for 4 for imaginary. Always totaling up to 5. And look, all your imaginaries, you see how they're 0, 2, or 4, showing you that you have 0 pair, or it always has to be even because remember they come in pairs. There's no way you should get a 3 or a 5 in this column whatsoever. Okay? And the answer, overall answer to this really is this right here, this table right here, where you would sit there and you can just list that off, right? I mean, give that as your answer right there. It encompasses all the different combinations possible. Okay? So let's try this again with example 6.